Why do we classify numbers? Why do we give them names like integers, irrational numbers, or negative numbers? For the same reason we classify anything. We want to make sure that everyone has an understanding of what specific numbers are called and what they mean. After all, there's a difference between 25 and negative 32 and 4 to the 6th power. In this Mometrics video, we'll provide an overview of numbers and their classifications. Numbers are our way of keeping order. We count the amount of money we have. We measure distance. We use percentages to indicate a sale. Numbers are an integral part of our everyday existence, whether they are whole numbers, rational numbers, or the first type of numbers we're going to look at, real numbers. A real number is any value of a continuous quantity that can represent distance on a number line. Essentially, it's any number you can think of. 50 is a real number. 1 billion is a very large real number. Real numbers encompass 3 classifications of numbers, which we'll talk about in a little bit. Whole numbers, rational numbers, and irrational numbers are all real numbers. Imaginary numbers are not real numbers. They are complex numbers that are written as a real number multiplied by an imaginary unit I. For instance, the square root of -1 calculates as the imaginary number I, and the square root of -25 is 5i. Even though imaginary numbers aren't real numbers, they do have value. Electricians use imaginary numbers when working with currents and voltage. Imaginary numbers are also used in complex calculus computations. So just because these numbers are called imaginary doesn't mean they aren't useful. Whole numbers are numbers that we count with. 1, 2, 3, 4, and 5 are all whole numbers. So are -17 and 0. Whole numbers do not have fractions or decimals. All whole numbers are called integers. Integers can be positive or negative whole numbers. All integers and whole numbers are part of a bigger group called rational numbers. This group also includes fractions and decimals. That means that 3/5 and 7.25 are rational numbers. Rational numbers can also be positive or negative. Rational numbers have opposites, which are called irrational numbers. These numbers can't be written as a simple fraction. Pi is the most famous irrational number. We have a close approximation of how to calculate pi, but it's just a close approximation. Pi is renowned for going on and on forever. That's why it's an irrational number. You can't easily write it as a fraction. Natural numbers are those that are positive integers, although there is some debate as to whether natural numbers start at 0 or 1. Negative numbers are, well, exactly that. They are the numbers below 0. There are several other number classifications as well. Numbers are divided into even and odd numbers. If you can divide a number by 2, that number is even. So 24, 36, and 74 are all even numbers because if you divide them by 2, you get 12, 18, and 37. Even numbers always end with 0, 2, 4, 6, or 8. Odd numbers can't be divided by 2 and leave a whole number. Any odd number divided by 2 will leave a fraction. So 17 divided by 2 is 8.5. 23 divided by 2 is 11.5. All odd numbers will end in 1, 3, 5, 7, or 9. Numerators and denominators form fractions, which are comprised of 2 integers. The number on top is the numerator, the number on the bottom is the denominator. The numerator, the top number, shows how many parts we have. The denominator, the bottom number, shows how many parts make a whole. Let's say you have 6 apples and 3 of the apples get eaten. The number of apples you have left over would be displayed as 3/6. You would then divide 3, the top number, into 6, the bottom number, to determine the percentage of remaining apples. In this case, the number is 50%. So that's our look at numbers and their classifications. From whole numbers to irrational numbers, we need to know what to call numbers so we can know what they mean.
Hey guys! Today we're going to take a look at the mathematical operations addition, subtraction, multiplication, and division. These 4 operations serve as the fundamental building blocks for all math, so it is crucial to have a solid understanding to build upon. Let's dive in. We use addition and subtraction to solve many real-world situations. Addition and subtraction are simply the mathematical terms used to describe combining and taking away. When we add, we are combining or increasing. When we subtract, we are taking away or decreasing. As a reminder, the symbol we use for addition is a plus sign. The answer to an addition problem is called the sum. The symbol we use for subtraction is a minus sign. And the answer to a subtraction problem is called the difference. Essentially, addition and subtraction are opposite operations. One adds value and the other deducts value. One strategy for visualizing these 2 operations is to use a number line. We will use a number line to illustrate the following examples. Let's imagine a situation that involves the sale of popcorn. For this scenario, let's assume that you are trying to raise money by selling bags of popcorn, and you start with 20 bags. When your first customer arrives, they wish to purchase 4 bags of popcorn. This means that your remaining number of bags will decrease. We can represent this situation with a simple equation that involves subtraction. We started with 20 bags, and we decreased by 4, or subtracted 4. Our subtraction equation is written as 20 minus 4 equals 16. On a number line, we can represent this deduction by starting at 20 and then moving backwards 4 units in the negative direction. Each jump backwards represents subtraction by 1. Now let's say you started with 20 bags of popcorn and ended up with 6 bags left at the end of the day. You need to replenish your stock in order to keep up your sales, so you make 4 more bags of popcorn. How many bags of popcorn do you now have available to sell? For this scenario, since we are looking at an increase of bags, we will use addition. This situation can be described using the equation 6 plus 4 equals 10. You had 6 bags initially and then combined that amount with 4 more bags. Now you have 10 bags in all. On a number line, addition is represented by jumps to the right in the positive direction. Each jump to the right represents the addition of 1 unit. So in this example, we would be starting at 6 and jumping 4 units to the right. We can see that we land on 10. It is important to notice that when using addition, the order of the values does not matter. For example, 10 plus 30 is the same as 30 plus 10. The placement or arrangement of the values has no effect on the outcome. Both arrangements would equal 40. However, the same is not true for subtraction. Does 30 take away 10 mean the same thing as 10 take away 30? Clearly not. We can see that the order matters when dealing with a situation involving subtraction. The technical term for this quality is known as the commutative property. Essentially, the property is true for operations where the values can move around, commute, and the outcome of the expression or equation will not change. The commutative property applies to addition, but not to subtraction. Another operation that also shares the commutative property is multiplication. Let's discuss multiplication together with division, as we did for addition and subtraction. Multiplication and division are similar to addition and subtraction in that they perform opposite functions. The function of multiplication is to represent multiple groups of a certain value, whereas division is designed to show the separating or subdividing of a value into smaller groups. As a reminder, the symbol we use for multiplication is a times sign. The answer to a multiplication problem is called the product. The symbol we use for division is a division sign, and the answer to a division problem is called the quotient. Multiplication is essentially a convenient and time-efficient way to show what's called repeated addition. For example, if you need to fill 30 bags of popcorn and each bag requires 60 kernels, it could take hours to count up how many kernels you need in total by just using addition. A faster and more efficient way to make this calculation would be to use repeated addition. Instead of counting each seed independently, we would group them up and add the groups together. The calculation would then become 30 groups of 60. This grouping, for the purpose of repeated addition, is the multiplication process at its core. 30 groups of 60 is written as 30 times 60, which is 1,800. So 1,800 kernels are required to fill up 30 bags of popcorn. Both addition and multiplication are commutative, because the order does not affect the answer. 30 groups of 60 gets us the same result as 60 groups of 30. Our last operation, division, can be considered multiplication's opposite. When we use division, we are essentially splitting up a large group into smaller subgroups. For our popcorn example, we can use division to answer the following question. How many bags of popcorn can I make using 1,800 kernels if each bag requires 60 seeds? This situation requires us to divide the large value, 1,800, into groups of 60. Each smaller subgroup will now represent a bag of popcorn. 1,800 divided into groups of 60 is represented as 1,800 divided by 60. In this case, the answer is 30. So 30 bags of popcorn can be made with our 1,800 kernels. As you can see, division is not commutative because the order of the values plays a crucial role in determining the answer. 1,800 divided by 60 is not the same thing as 60 divided by 1,800.
Hey guys, welcome to the Symmetrics video on fractions. Fractions can be simple or complex. In this video, we'll cover different types of fractions and how to add fractions with different denominators. So, what is a fraction? A fraction is a part of a whole, which means a fraction can never be a whole number. Think of it like this. Our circle is divided into 8 equal pieces. Let's say 3 pieces were filled in. That means that 3/8 of our circle is filled in. The top number is called the numerator. And our bottom number is called the denominator. When saying fractions out loud, the denominator will usually be spoken as the ordinal version of the number. You would say 1/8 instead of 8, or 1/3 instead of 3. Let's take a look at a list of our denominators and see how we would say them. As you can see, there are a couple of exceptions. If our denominator is 2, you could say half instead of second. Or if our denominator is 4, you can say quarter instead of fourth. But either one is acceptable. Hopefully that helps you to understand how fractions are defined and also how to actually say them out loud. But there are different types of fractions. Let's take a look at those. First, we have a proper fraction. A proper fraction always has a numerator, which we looked at, that is smaller than the denominator. Our example that we used before, 3/8. So our numerator, 3, is smaller than our denominator, 8. Some other examples of proper fractions include 4/5. An improper fraction is the opposite of a proper fraction in that the numerator is larger than the denominator. So while 3/8 is a proper fraction, 8/3 is an improper fraction because the numerator is larger than our denominator. Improper fractions are always equal to or greater than 1. That means that 9/9 is an improper fraction since it's equal to 1. There are also mixed fractions, which contain a whole number and a proper fraction. Here's an example. Note that the whole number 2 is followed by the proper fraction 3/4. We also have equivalent fractions. Equivalent fractions are 2 different fractions that name the same number. For example, 6/8 and 3/4 look different, but they're the same. 3/4 is just a simplified or reduced version of 6/8. To simplify 6/8, you just divide the numerator and the denominator by 2 to get 3/4. Now that we know the different types of fractions, we can explore how to add them. If two fractions have the same denominator, adding is a breeze. You just add the numerators together, and that gives you the answer. For example, so notice what we did to get 3/4. All we had to do was add from our first fraction the 1 from our numerator, and from our second fraction the 2 from our numerator. Add them together to get 3, and we just bring over our 4 from the denominator. Simple. But what happens if the denominators are different? Well, in that case, you have to convert the denominators to be the same. So let's take a look at an example. You can't really simplify 3/8 into anything that would easily add with 1/2, but we can do something with 1/2 that we could easily add with 3/8. And that's multiplying 2 by 4, which would give us 8. But whatever we do to our denominator, we also have to do to our numerator. So that would look like this. So our equation now becomes 3/8 plus 4/8 equals 7/8. Subtraction works the same way. If you're subtracting fractions with the same denominator, you can just subtract the top numbers, like in this example. So in this example, all we had to do was subtract our top numerators here, which gave us 2/4, which simplifies to 1/2. Simplifying numbers just makes them easier to work with. But if you're subtracting with a different denominator, you have to make the denominators match. For example, so in this example, 3/8 minus 1/4 is equal to x. We're kind of looking at a same issue like we did over here. We need our denominators to match. So we need to find out what can we do to make our denominators match. Well, in this case, we can multiply 4 times 2. But remember, we have to do the same thing that we do to the denominator, we must do to our numerator. So we can multiply it times 2, and then here's what we get. So once we multiply our second fraction here by 2, we get 3/8 minus 2/8, which gives us 1/8. So these problems were pretty easy because they had either the same denominator or were just really easy to convert. But let's look at one more equation that's a little trickier. So at first glance, it doesn't look like these numbers have much in common, such that we would be able to multiply or divide 4 by anything to get 7, or 7 by anything to get 4. So a lot of the times when you have problems like this, what you end up having to do is multiplying this fraction by the denominator of the other fraction. And likewise, we would multiply this fraction by the denominator of this fraction. So here's what that looks like. So after our multiplication, we end up getting a common denominator, which is 28. So now all we have to do is add our numerators together, which that gives us 45 over 28. And that's our answer. With this calculation, we found the least common denominator. The least common denominator is the smallest common number between denominators. Anytime you perform a calculation with different denominators, you must find the least common denominator to solve the problem.
You may have heard a math teacher or two say math is a language. If that is true, then algebraic rules and notation should be considered the grammar and punctuation of the language of math. Some students who struggle with math are confused by how to apply the rules and interpret the notation. In this video, we will focus on the notation and interpretation of exponents. This video will focus on the meaning of exponents that are natural numbers, also referred to as counting numbers, which are 1, 2, 3, things like that. Other types of exponents are interpreted differently and will be covered in other videos. Let's start by quickly reviewing some terminology. An exponent is written as a superscript on a number or algebraic expression, which is referred to as the base. There are a few ways to verbalize a power. This simple example can be read as 5 squared, 5 to the second, 5 raised to the second power, or 5 raised to the power of 2. In any case, the exponent should be interpreted as repeated multiplication. Whatever is defined as the base should be multiplied by itself however many times the exponent implies. For example, 5 squared equals 5 times 5. This can then easily be evaluated as 25. Let's look at some more examples. 7 cubed. This time the base is 7 and the exponent is 3. This can be read as 7 to the third or 7 cubed. Raising a base of 7 to the power of 3 means to multiply 7 by itself 3 times. 7 times itself 3 times equals 343. Let's try another one, but this one will look a little different. -2 squared. It is important to point out that parentheses are being used with this example to define the base. -2 is being raised to the second power. The interpretation is the same. Simply multiply -2 by itself twice. Multiplying two negative numbers using parentheses results in a positive value. But if we were to take the parentheses away and instead say -2 squared, then our answer would be -4. Why? Because the 2 is squared before the effects of the negative can take place. So we have 2 times 2 equals 4, and then the negative affects it. Let's try another one with negatives. -5 cubed. This is equal to -5 times -5 times -5, which gives you -125. Powers of 10 are used frequently in math and science applications. Scientific notation uses powers of 10 to express very large or small values in an efficient and organized manner, but we'll dive into that topic in another video. Exponents are also used to raise algebraic expressions to powers, but the meaning is the same. Multiply whatever the base is by itself, however many times that is indicated by the exponent. Here are a few examples. X cubed is equal to x times x times x. As you can see, the notation x cubed is a more efficient way to write the expanded version of x times x times x. 2x cubed is equal to 2 times x times x times x. Notice that the base here is x. Adding parentheses to an expression changes the meaning. If you put in parentheses, 2x cubed means 2x times 2x times 2x, which is equal to 2 times 2 times 2 times x times x times x, which when you simplify that, gives you 8x cubed. Let's try one more example before we go. X plus 2 squared. Once again, the parentheses here are used to define the base to be x plus 2. The exponent of 2 instructs you to multiply this base by itself twice. So it equals x plus 2 times x plus 2. Multiplying these two binomial expressions results in the quadratic expression x squared plus 4x plus 4. So, as long as you can identify the base, the multiplication of that base by itself becomes pretty straightforward. As mentioned, the interpretation of notation in math is half the battle. Practicing the basics is key in order to gain confidence for more complicated math content.
Hi, and welcome to this video about angles. Let's start by defining a ray. A ray is a line with a single endpoint that extends infinitely in one direction. If we take this ray and add another ray to it that has the same endpoint, we've created an angle. We've also created a vertex, which is the point where two rays meet. You can think of it as a corner. We usually see vertices whenever lines meet or in polygons like triangles and quadrilaterals. Sometimes we have many angles, so in order to tell them apart, we have a system for naming them. Here's our simple angle again, but with a few points added on the rays. Now we can refer to our angle as angle ABC. When naming angles with 3 letters, the vertex point must be in the middle. Here, B is the vertex, so the B goes between the A and the C. We can actually call this angle CBA, and it is just as correct. If the point that is the vertex is only a part of one angle, then we can use a shorter name. In this case, we could also call this angle B. Be careful though, because sometimes a single point can be the vertex of multiple angles, like this. In this case, we'd have to call the angles by their long names, because point B is the vertex of angles ABC, DBC, and DBA. If we asked someone to just look at angle B, they wouldn't know which of these we meant. So it's important to be precise when dealing with more than one angle. Sometimes angles will be labeled with numbers inside the arc, like this. Now we have an additional name for this angle. We now call it angle 1, or we can call it angle ABC, or we can call it angle B. Since most of us have 3 names, it's only fair that angles have a bunch too. But most of the time, we like to use letters to name our angles, since the numbers could be confused with the measure of an angle. Sometimes you'll see lowercase letters instead of numbers, or Greek symbols like theta or alpha. Speaking of measuring, remember the protractor? We use it to measure angles. If we were to place one on our trusty angle, we would find that it measures 45 degrees. If we wrote this out, we would write it like this. The measure of angle ABC equals 45 degrees. The measure of an angle is important in classifying angles, as we're about to see. Let's look at a variation of our 2-ray angle, but this time let's make it so that they are perpendicular to each other, which means the angle between them is 90 degrees. Here, we've created a right angle. Notice that it has a different angle symbol than our first angle. Instead of an arc, it has a square. Whenever we see an angle with that square, we know it is exactly 90 degrees. We most often see right angles in squares, rectangles, and right triangles, but they can appear in other places too. When an angle has a measure that is smaller than 90 degrees, it's called an acute angle. Our original angle would be part of an acute triangle, since it measures 45 degrees, which is less than 90. If we make an angle so that it has a measure that is greater than 90 degrees, we create an obtuse angle, which looks like this. In this case, angle ABC has a measure of 140 degrees, which is greater than 90. Obtuse angles also have to be less than 180 degrees. Those are the 3 main types of angles as determined by measure, but there are 2 more oddballs we need to know about. The first is a straight angle. It looks like a straight line and it has a measure of 180 degrees. When it's drawn like this, we can see that angle ABC does exist and has a measure of 180 degrees. This is a useful thing to know because we'll need it to understand linear pairs later on. But before we get to that, let's look at the other oddball. This one doesn't look like an angle at all, but in fact, it's called a full angle. Imagine we rotated point A counterclockwise, with point B staying where it is, until it lined up with point C again. How many degrees is that? It's all the way around the circle, which we know is 360 degrees. Remember our straight angle? What if we drew that but added another ray sticking out of it, like this? If we know that angle DBC is 55 degrees, and we know that angle ABC is a straight angle, and therefore 180 degrees, we can actually find angle ABD. How? By taking the whole straight angle, ABC, that measures 180 degrees and subtracting the smaller angle, DBC, that measures 55 degrees. 180 degrees minus 55 degrees equals 125 degrees. This is called a linear pair. 2 angles, ABD and DBC, combine to form angle ABC, which is a line. And because the 2 smaller angles add up to 180 degrees, we can also say that they are supplementary angles. Something very similar happens with right angles. Here's our right angle from before, but with another ray in the middle. Angle DEF is a right angle. We can see that angle DEG and angle GEF together completely fill angle DEF, which means they add up to 90 degrees. So if we know one of the two angles, we can find the other one by subtracting its measure from 90 degrees. For instance, if angle DEG is 30 degrees, then we know that angle GEF is 60 degrees, because 90 degrees minus 30 degrees equals 60 degrees. Angles that add up to 90 degrees are called complementary angles. Let's go back to our obtuse angle one more time. There's one more type of angle that's been hiding in plain sight that we need to be aware of. We can see that angle ABC is an obtuse angle, which means it's more than 90 degrees and less than 180 degrees. But what about the other side? This is called a reflex angle. It's always more than 180 degrees and less than 360 degrees. Every acute, right, and obtuse angle has a reflex angle. Next, let's take a look at where we'll see some of these angles in the wild, or at least in geometry problems. Let's start by looking at two lines that intersect. In this case, we've numbered the angles. Whenever we see a figure like this, if we know any of the angles, we can determine all of the others. So if angle 1 measures 130 degrees, we can figure out angle 2, because those two angles together form a line and are a linear pair and supplementary. So angle 2 must be 50 degrees. The same works for angles 1 and 3. And then we can use what we know about angle 2 to pair it up with angle 4 to find that angle. When it's all said and done, it looks like this. Notice that the angles opposite one another have the same measure. These angles are called vertical angles, and they're always congruent, which is geometry speak for having the same measure. Now, let's look at three lines intersecting. This is called a transversal. Once again, we've numbered the angles and there are red arrow marks on two of the lines, indicating that they are parallel. A transversal doesn't have to have parallel lines, but when it is, it allows us to know a lot about the 8 angles created by the intersecting lines. But before we get to that, let's look at the 8 angles. We can see they are in two groups of 4, angles 1 through 4 and angles 5 through 8. Angle 1 is in the top left position in the top group of angles. If we look at the same spot in the bottom group of angles, we see that angle 5 is in the top left spot for that group. That means that angles 1 and 5 are corresponding angles. So angles 2 and 6 are also corresponding angles because they're in the top right spot for their respective groups. Angles 3 and 7 are also corresponding, as are angles 4 and 8. In a transversal, when there's a pair of parallel lines, corresponding angles are congruent. When the lines are not parallel, the corresponding angles are not congruent. In the case of our diagram that does have parallel lines, if we know that angle 2 is 55 degrees, we then know that angle 6 is also 55 degrees. And once we know that, we can use what we learned about vertical angles and linear pairs to find all the others. That's all we need to know to find our angles, but there is some more location-based vocabulary we need to be aware of with these types of problems. Interior angles are the angles between the parallel lines. In this case, that's angles 3, 4, 5, and 6. The exterior angles are the ones that, you guessed it, are not between the parallel lines. So angles 1, 2, 7, and 8 are exterior angles. Alternate angles are angles that are on opposite sides of the line that cuts across the parallel lines. And same-side angles are angles that are on the same side of that line, of course. In questions about the two groups of angles, this is used to combine interior or exterior with alternate or same-side angles. The question will always relate to the other group of angles. Something like, what is the alternate interior angle for angle 3? We would look to the other group of angles, then to the other side of the intersecting line, and then find the only angle that is an interior angle, which would be angle 6. The same side interior angle for angle 3 is angle 5. That's a lot to absorb in a small amount of time. Try these questions to see if it's sunk in. What is the alternate exterior angle to angle 8? The answer is angle 1. What is the same side exterior angle to angle 7? The answer is angle 1. What is the corresponding angle to angle 5? The answer is angle 1.
Hi and welcome to this video about polygons. In this video, we will explore 4 things. 1. What polygons are. 2. the different parts of a polygon. 3, ways to classify polygons. And 4, how to determine the number of diagonals in a polygon. The term polygon is derived from the Greek words polis, meaning many, and gonia, meaning angle. So polygons have many angles. First, let's explore how polygons are constructed. Consider the geometric point, represented by a dot. The point is zero-dimensional. It has no length, width, height, nothing. Now let's consider two connected points. This is called a line, or a line segment. A line segment is one-dimensional. It has length, but no width or height. When multiple line segments are connected end to end, polygons such as this can be formed. Polygons are two-dimensional. They have no thickness, like this. In order to be a polygon, the shape must be closed. In other words, every endpoint must be connected to another endpoint. This figure is comprised of connected segments, but the result is not a polygon. This shape is closed, but not made up of any connected segments, so it is also not a polygon. A polygon is defined as a two-dimensional closed shape composed of line segments. The sides of polygons are called edges, and the angles created where the edges intersect are called vertices. Polygons also have as many edges as vertices. Polygons are named by the number of edges they have. This polygon has 3 edges, 3 vertices, and is called a triangle. The triangle has the smallest number of edges and vertices of any polygon. It is impossible to create a two-sided polygon. Some common polygons are quadrilaterals, which have 4 sides, pentagons, which have 5 sides, hexagons, 6 sides, heptagons, 7 sides, octagons, 8 sides, nonagons, 9 sides, decagons, 10 sides, and dodecagons, which have 12 sides. Though polygons with any number of edges have names, the general n-gon is typically used for all other polygons, where n represents the number of sides. For instance, a 30-sided polygon is called a triacontagon, but it's often simply called a 30gon. Polygons can be regular or irregular. Regular polygons have congruent edges and congruent vertices. For example, this is a regular quadrilateral. The edges are the same length and the vertices have the same measure. This is an irregular quadrilateral. The vertices have the same measure, but the edges have different lengths. This is an irregular quadrilateral. The edges are the same length, but the vertices have different measures. This is an irregular quadrilateral. Neither the edges nor the vertices have the same measure. Polygons can also be convex or concave. When one or more vertices of a polygon measures more than 180 degrees, the result is a concave polygon. For example, this is a convex hexagon. All the vertices measure less than 180 degrees. This is a concave hexagon. One vertex measures more than 180 degrees. Now remember, only polygons with 4 or more sides can be concave because it's not possible for a triangle to contain an angle measuring more than 180 degrees, which is a straight line. Concave polygons cannot be regular because all the vertices will never be the same measure. Polygons also contain diagonals. Diagonals are line segments joining 2 vertices that are not next to each other. As you can see here, this irregular convex pentagon has 5 diagonals. This is an irregular concave pentagon. It also has 5 diagonals, even though the concavity causes diagonals to lie outside the polygon. Triangles do not have diagonals because there is no way to connect two vertices with segments that are not edges. Now that you know the basics of polygons, let's use the diagrams to figure out a formula for finding the number of diagonals in any polygon. In this case, the number of diagonals connecting to each vertex is 2, which is 3 less than the number of vertices, 5. 2 diagonals connect to each vertex. This is true of all diagonals of all polygons. A nonagon has 9 minus 3 equal to 6 diagonals connecting to each vertex. The number 3 is not arbitrary here. From any vertex, diagonals cannot connect to the vertex itself or to the vertices that they are 1 away from, because it would be edges. That makes 3 vertices from every vertex that aren't included. To generalize this, we'll use n minus 3, where n is the number of vertices of the polygon. Now each vertex has the same number of diagonals connecting to it, so in this case we can see that the total number of diagonal connections to vertices is 5 times 5 minus 3, which is equal to 10. In general, we can say the total number of diagonal connections is n times n minus 3. When we figure out this total, though, we are counting each diagonal twice because diagonals have 2 endpoints. In order to figure out the number of unique diagonals, we need to divide our total by 2. In our pentagon, this looks like 5, which corresponds to our diagram. Therefore, for any size polygon, our equation can be written as this: n times parentheses n minus 3 all over 2, or divided by 2. Conceptually, this can be remembered as Using our formula, we can determine the number of unique diagonals in, for example, a 17gon, which is equal to 119 unique diagonals. We can also see algebraically that triangles have no diagonals. We can also figure out how many edges or vertices a polygon has by the number of unique diagonals. Suppose a polygon has 44 unique diagonals. How many edges does the polygon have? Alright, so here we are at an answer. N, the number of edges the polygon has, is either equal to 11 or -8, because what we want to do is we want to make sure that we end with the result of 0, which means that n somewhere has to be 11 or -8 in order to get us multiplying 0 by another answer, resulting in 0. Since n can't be negative, because we can't have negative edges, it can't be -8. So we know that our answer is 11. The number of edges is 11, making it an 11gon.
Most of us learned how to draw a circle in math class using a compass. All we needed to know was where to put the center of the circle and the measure of the radius to set on the compass. Then we held the compass steady at the center and rotated the pencil part all the way around to draw our circle. If we drew it on graph paper and looked closely, we could probably find a few specific points on our circle. But what if we don't have a compass, or graph paper, or even the radius of the circle? What if we are only given the center of the circle and one point on the circle? Can we find the other points on the circle? The answer, of course, is yes. And that's what we're going to do today. Let's start by looking at the equation of a circle. X minus h squared plus y minus k squared equals r squared. Wow, that's a lot of variables. The x and the y are pretty standard, but the others might not be familiar. The h and the k together make the center of the circle at the point hk. The r is the radius of the circle. So if we have a circle with a center at the point 2, 3 and a radius of 5, our equation would look like this. X minus 2 squared plus y minus 3 squared equals 25. We simply plug in the values for h and k and then square the radius for the right side of the equation. Be careful when h and k are negative though. For instance, if the radius is 4 and the center of the circle is at -4, -5, and we substitute into our equation, we have to deal with subtracting negatives. X minus -4 squared plus y minus -5 squared equals 4 squared. Those two negative signs in a row cancel, and we end up with x plus 4 squared plus y plus 5 squared equals 16. When the center of the circle is at the point 0, 0, also known as the origin, our equation gets simpler. X minus 0 squared plus y minus 0 squared equals r squared becomes x squared plus y squared equals r squared. Simple, right? But we've got a little bit carried away. Let's get back to our problem. If we're given the center of a circle and one other point, can we find 3 other points on a circle? Let's do an actual problem to see how we should get this done. Find at least 3 other points on a circle that has a point at 2, 6 and its center at -2, 3. So our point is going to be at 2, 6. And our center is at -2, 3. The first thing we need to do is find the radius of the circle. We can do this by plugging in everything we know into our equation for a circle. Since we know the center is at -2, 3, we know that h equals -2 and k equals 3. Since we know a point on our circle, we can use x equals 2 and y equals 6. We plug it all in and it looks like this. So the formula for a circle is x minus h squared plus y minus k squared equals r squared. So our x and y comes from our point that we're given, and our center is our h and k. So x is going to be 2 minus h is -2 squared plus y is 6 minus 3 squared, and we're not given r, so it equals r squared. We deal with our subtracting and negative problem to get this. 2 minus -2 is the same as 2 plus 2. So we just replace that minus a negative with a plus sign, and then everything else stays the same. 6 minus 3 squared equals r squared. Then we evaluate what's in each set of parentheses. 2 plus 2 equals 4. So we have 4 squared plus 6 minus 3 is 3. 3 squared equals r squared. We apply our exponents. 4 squared is 16. 3 squared is 9 equals r squared. And then we're going to add them and solve for r. So 16 plus 9 is 25 equals r squared. We'll square root both sides and get that r is equal to 5. Now what? How can we use this information to find more points on our circle? We're going to use a different kind of compass to do that. Let's get out a piece of graph paper and plot what we know so far. Since we know our radius, we can travel north, south, east, and west from that point exactly 5 units to find more points. Moving along the compass points is easy on our graph paper, and since the radius is the distance from the center of the circle to all points on the circle, we know we'll end up on our circle when we travel 5 units. Look at all those points we found. Going north 5 units, we found -2, 8. Going west, we found -7, 3. Going south, we found -2, -2. And going east, we found 3, 3. 4 points. 1 more than the problem asked us to find. And we're not done yet. We can find even more points if we want, since the given point isn't one of our 4 compass points. If we look to see how far over and up that point is from the center, we can find more points that are the same L-shaped distance away. Here we can see that 2, 6 is 4 units to the right and 3 units up from the center of the circle. So I can draw L shapes from the center that move 4 units left or right, and then 3 units up and down to find more points. We found 3 more. On the left or west side, we found -6, 6 and -6, 0. And below our given point, we found 2, 0. Altogether, we now have 8 points on our circle, including the given one. And if we're willing to do some heavier math, we can find any of the infinite number of points on our circle. Since we're on such a roll, let's try that too. First, we need to establish our domain so we can know what x values we can pick. The leftmost x value on our circle is our west point at -7. Our rightmost point is our east point at +3. So our domain is x is greater than or equal to -7 and less than or equal to +3. So we can pick any x value from -7 to 3 to find its corresponding y values on the circle. Yes, it's plural because there will be 2. So let's pick x equals -4 from our domain. Now all we have to do is plug that into our equation for this circle and solve for y. So we're using the x value -4. And remember, our center is at the point -2, 3. So now all we're going to do is plug that into our equation for the circle. So remember, that's x minus h squared plus y minus k squared equals r squared. So our x value is -4 minus h is -2 plus y, we don't know what that is, that's what we're trying to solve for, minus k, which is 3 squared. And we forgot to write this, but our r, remember from earlier, is 5. So it's equal to 5 squared. So -4 minus -2, that's the same as saying -4 plus 2. So let's rewrite it that way. -4 plus 2 squared plus y minus 3 squared equals 5 squared. Then we'll simplify this to -2. So -2 squared plus y minus 3 squared equals 5 squared. And now we're going to simplify our exponents. -2 squared is 4, plus, we'll leave this part alone for right now. We'll come back to that later. Y minus 3 squared equals 5 squared is 25. Now we'll subtract 4 from both sides. This gives us y minus 3 squared equals 21. And we'll take the square root of both sides. That leaves us with y minus 3 is equal to plus or minus root 21. And all we have to do is add 3 to both sides. So our answers are y equals plus or minus root 21 plus 3. So the two values are the square root of 21 plus 3 and the negative square root of 21 plus 3. If we're plotting those points on a graph, we can estimate their value by using a calculator to find that our y values are approximately 7.58 and -1.58. So we can graph those too. Now we're up to 10 points on our circle. Can you find any more? Pause this video now and try. The answer for all the integer values of x will appear shortly after unpausing. Here are the other points on the circle with integer x values.
It's been said that a picture is worth 1,000 words. This is true of the many different ways that data can be transformed into visual representations for easier interpretation. Data in and of itself can be difficult to explain, but when it is carefully organized, patterns can be revealed, or it may become apparent that no patterns exist. Either way, both results are meaningful. Advances in technology enable us to collect and track data like never before. An interpretation of data is simplified with the use of graphs. Data is collected for many reasons, ranging from simple consumer surveys to track preferences, to election polling, to predict the winner of a political office. Graphs are used to make that data easier to digest or comprehend. Before we get to the graphs, you should know that there are different types of data that can be collected. The first one we'll talk about is qualitative data. This data would result from a survey that groups respondents by category. For example, you can survey students in your school and ask them to report their eye color, gender, area code, and favorite movie type. These categories provide information for your study. In this case, maybe you're wondering whether there is a relationship between the number of blue-eyed sci-fi fans living in a particular area code. Well, you may be able to detect a pattern in the counts, or percentages, of qualitative data by category. Graphs that are used to depict qualitative data are pie charts and bar graphs. A pie chart looks exactly like what you might expect, a pie. A circle representing 100% of a particular variable of interest is divided into categories. Segments of the pie represent a percentage of the whole. Pie charts can also show counts. In this example, 6 people, or 30% of the respondents, favored romantic movies. Bar charts also show counts or percentages by category, but in a different way. It looks like a city in the distance with skyscrapers at varying heights. This bar chart shows categories on the horizontal axis with the associated counts on the vertical axis. Next, we have pictographs. As the name suggests, a pictograph provides visual context. Visual cues and images are used to represent the data, and keys are provided to tell you what each image or symbol represents. In this survey of student fruit preference, apples took the lead with 20 students reporting them as their favorite. Another type of data that can be collected is known as quantitative. Unlike qualitative data, you can do math with quantitative data because it is numeric in nature. For example, what if you're interested in the average AP statistics score of the graduating class of your high school? Gathering reliable data may be the trickiest part of your study, but a histogram can relay trends in the results with precision. A histogram resembles a bar graph, with the exception of spaces between the bars. There's a range of numeric values displayed on the horizontal axis, and the counts of students are displayed on the vertical axis. The pattern of scores may appear somewhat symmetric, which is typically referred to as normally distributed. This would suggest that most students scored in the middle of the range, and that there were some high achievers and others who were not so successful. A histogram could also show a skew to the right or left, which may reveal information about overall student understanding. Scatter plots show data points for two quantitative variables on the same graph. The pattern revealed could show an association between the two variables. The data is analyzed with respect to direction, form, and strength. Direction can be positive if a rising pattern is seen in the data, or negative if a falling pattern is seen. The form of the scatter plot identifies whether the data appears somewhat linear, curved, or cone-like in shape. Strength associates how tightly the points are gathered. An example of a strong positive, somewhat linear pattern could be revealed in a scatter plot of shoe size versus height of male high school students. Because typical male students continue to grow during the high school years, the data for all male students would likely show underclassmen data points at the lower end of the scatter plot and upperclassmen represented at the higher end. Data points that do not fit a recognizable pattern are referred to as outliers. Finally, a scatter plot with no pattern at all is also of interest to prove no association between the two variables. Regression analysis can be performed on scatter plot data that has been characterized as strong linear in shape and either positive or negative in direction. This regression line serves as a predictive model only for estimating other points of interest within the range of the data set. Line graphs are very useful to recognize how patterns in data sets change over time. Unlike a linear regression model that runs through a set of points, a line graph connects the data points. The graph of mobile phone sales over time shows an overall increasing pattern. However, there was a noticeable dip in the sales between 2011 and 2012. Graphing multiple variables together in a line graph can also be very informative. For example, suppose temperature and rainfall amounts in a particular region were graphed simultaneously. As can be seen, contrasting weather patterns are revealed. Finally, stem and leaf charts contain actual data values. The pattern revealed is similar to that of a bar chart that has been rotated clockwise 90 degrees. The stem of the chart lists the digits of an indicated place value vertically. In this example, the stem represents the tens of a data set of ages. The leaves branch outward with the digits of the ones place for each age in the data set. A key should always be part of the graph so the data can be interpreted correctly. This data set shows a pattern that seems to be skewed left towards the younger ages. There are 19 people under 20 and only 7 people over 50.
Hello, and welcome to this video on domain and range. In this video, we will see what domain and range are and how to find the domain and range of a function. Remember, a function is a relation between two sets of numbers, an input and an output. Each element of the input produces a unique element of the output. The domain of a function is the set of all possible inputs of a function. This means that it is any number you can plug into a function. For most functions, this will be any number you can plug in for the letter x. Almost every time, your domain will be all real numbers, except for a special few cases like square root functions and rational numbers. The range of a function is the set of all possible outputs of a function. Typically, this will be represented by the letter y, or f of x. The range is any number that you can get when you plug in any number for x. Let's look at a simple linear function, y equals 4x plus 3. We're going to find the domain and range using just the equation by looking at a graph and by looking at a table. Let's think about this algebraically for a minute. The domain is any number we can put in place of the x. You could put 1, 2, -7, 84, or any other number in place of the x. This means that the domain is negative infinity is less than or equal to x is less than or equal to positive infinity. Another way to say this is that the domain is the set of all real numbers. What about our range? Well, if I plug in 1 for x, I get 7, and if I plug in 2 for x, I get 11. But I can also plug in 1.5 for x, which would give me 9, or 1.25 for x, which would give me 8. I can plug in any decimal number, so for this equation, I can also get out any number for y by searching for the right x. The range of this function is also the set of all real numbers. Now I want to check this graphically. If we graph this function, we see that it is a line. Lines continue across every value of x and every value of y. This matches up with what we found out by thinking through it algebraically. This further proves that the domain and range are both the set of all real numbers. Now let's look at a table of values for the first 4 terms of this function. In this case, we are only looking at a portion of the function, so our domain of values would be 1, 2, 3, and 4. And our range of values would be 7, 11, 15, and 19. Let's try a couple of examples. What is the domain and range of the function y equals x squared minus 4x plus 3? The domain is the list of numbers that can be plugged in for x. You can plug in any number for x, so the domain is the set of all real numbers. What about our range? Let's figure this out by looking at a graph of the equation. Remember, our range is every possible value for y. If we look at our graph, we see that it is a parabola that opens up with a vertex at 2, -7. This means that our range is y is greater than or equal to -7. Let's try one more example, this time using a table for the function y equals 2x minus 1. What would be our domain and range given this table? Our domain would be 7, 14, 21, and 28, and our range would be 13, 27, 41, and 55. If we wanted the domain and range for the whole function, we would consider what numbers we can plug in for x and what corresponding y values we would get. Well, we can plug in any number for x, and it is a linear function, so we can get any number for y. Therefore, the domain and range of this function is all real numbers. Remember, if you are finding the domain and range of a function algebraically, think about what numbers you can plug in for x and the resulting numbers you will get for y. If you are finding the domain and range given a graph, follow your finger along the graph to see what x values it covers and what y values it covers. Finally, if you are looking at a table, the domain is the list of numbers inputted for x, and the range is the list of numbers that are the outputs of those x inputs, the numbers in the y column. I hope this video on domain and range was helpful. Thanks for watching, and happy studying.